Yeah, so this is about a recent work with Eunjung and Sang from KAIST. The title is Constructive Algorithm for Pathwidth of Matroids. So I'll first give some background, like the basic notation and some history and what has been done, and then so the background will be about the half the talk, and about 10 minutes or so I'll give a very rough. I'll try to convey some feel about how the algorithm will work, and if I have time, then I'll mention some application of the algorithm. So, okay, here is a quick reminder of what Matroid is. So actually, the algorithm itself doesn't rely on the Matroid itself. So we don't even use the word Matroid in the most of the technical section. But yeah, because it's about Matroid, just let's begin with what Matroid is. So a pair of two objects, E and I, is called Matroid if they satisfy the following. So E is called a ground set. It consists of elements, and I is a family of subset of the elements in the ground set. So if I satisfies the following three properties, then this pair is called Matroid. So what is the property? So first, the empty set should be in this family. Secondly, if Y is in this family I, then for any subset, for any subset X, for any subset of Y should be again in this family. And for any two subsets from this family, if the size of X is smaller than the size of Y, then you can pick some element from Y so that you can augment X with this new element Y, and this again belongs to the set I. So this set I is called independent set, and that, the obvious object that satisfy these three conditions is the set of column vectors in a matrix, right? So obviously the column vectors of a matrix forms a matroid with the independent set defined as an independent set of column vectors, and the matroid which can be represented as a matrix, the matroid which is represented as a matrix even has a name, which is called so a matroid set is representable in a field F if there is a way to have vectors in a vector space over this finite field F, and there is a way to bijectively match the elements of this ground set and the vectors in this and the vectors in this and the vectors. And this bijection should satisfy that whenever a subset here is an independent set, then the corresponding vectors is an independent set in the usual sense. So if a matroid has a way to be represented by vectors in this way, it's called a representative in a field F. And if the vector representation is already given, we say it's a represented matroid. So what we are interested in this work is represented matroid. So you can just forget about matroid, but you can consider that vectors are given as a representation of your matroid. So this is the central problem of this work. So at least I hope that you can remember this problem at the end of this talk, even if you forget other things. So let's fix field F, and we assume that this field is finite. So the input of this vector arrangement problem is n vectors, v1 up to vn, of dimension r, dimension r vector space. And you are given a positive integer. And the goal is to find the linear layout, like permutation, linear ordering, of these vectors, which satisfies the following property. So what we want is that when you have a linear ordering of these vectors, you want the order of the gap for any of the gap here between vectors should be small. So what do you mean that the order of this gap is small? So the vector space, the subspace spanned by the first I vectors, and the subspace spanned by the rest of the vectors on the right side of the gap, and look at the intersection of them. And we want the dimension of these two, the intersection of the two spaces is bounded by K.
Should let's say yi plus 1, or instead of y feature?
Sorry, here it should be I plus 1. Yeah. Yes.
Okay.
Thank you.
And should it be plus or commas in the first line?
Plus, yeah. Yeah, so actually it's the same, but yeah, it should be plus. Sorry. I tried not to make too many typos, but you have typos. Okay, so the problem is clear, right? So this is a problem that we consider through the whole work. And such a linear layout is said to have width most k, and also this is equivalently a path width of the matroid represented in the over the field F. So here you had a linear layout of the vertices, so it's kind of caterpillar. And instead of having caterpillar, you can allow a tree in general. And then you obtain the definition of branch width. So what is branch width? So here we want to find the kind of partition of the vectors. So you can consider it as elements of the matroid, but let's just talk about vectors. That's much easier. So you want to kind of have a partition of the vectors and want to represent the partition in a hierarchical way using this tree structure. And every partition represented by the edge of the tree, you want this partition to have small order in the sense that this has a small order. So again, more formally, we are given n vectors again in this vector space, and we consider finite field, and want to find a subcubic tree, and we want to match the leaves with the given vectors in a bijective way, such that at every bipartition given by edge of the tree, the order is MOSK, and the order is the subspace of the one of subspace spanned by the one part of the vectors and the other part of the vectors, and you look at the intersection of them. This is called a branch decomposition, and you can extend this definition of branch decomposition for any matroid with different way of defining ordering, which is just generalization of this definition. Okay, so matroid is interesting. One obvious way for us is we are very familiar with graphs, and matroid is natural extension of graphs in several ways. So just let's look at one example which is relevant here. So I kind of assume that you know path width of graphs. The path width of a graph is the same as the path width of cycle matroid of G prime, where G prime can be obtained in a very simple way. So suppose this is graph G. We double every edges of G and add one apex vertex, which is adjacent to with everyone in G with double edges. So this is very simple construction, and then we have this relation. And okay, again, the branch width of graph is the same as the branch width of a cycle matroid of G, if G is not a tree. So if G is a tree, then this relation doesn't hold. So just a quick reminder, or you can try, if you are not familiar with matroid, this is a very simple exercise. So cycle matroid of G is defined as an element and the independent set, where the ground set takes the edges of G as the elements, and the independence is the forest. So this is a cycle matroid of G, and this is, you can check that this satisfies the three properties of the matroid. Okay, so the problem of computing pathwidth and branch width is interesting for matroid point of view, and also it's interesting because it's an extension of the width parameter that we are interested as algorithm designers for graph theory. So what is known about the algorithm for computing pathwidth and branch width? So when k is a fixed constant, there is a polynomial time algorithm. I mean XP algorithm, which runs like n to the O of k time. And this algorithm works for general matrices. So the next question is whether we have FPT algorithm for matrices, and if it's not possible, then which kind of matrix allows FPT algorithm for pathwidth and branch width? Okay. So the situation for computing pathwidth for matroid is kind of similar to the state of art for pathwidth of graphs like 20 or 25 years ago. So let's look at how a big machinery can help for this pathwidth problem. So this is kind of a schematic diagram for pathwidth problem via minor testing. So I guess many of you are already familiar with this schematic. So let's define GK as the graphs which have pathwidth most k, and this is minor closed. So if you know the definition of minor, then it's again an easy exercise. And let's define F. Let's define F as the minimal graphs, minimal in the sense of matroid, in the sense of minor relation. So it's a minimal graphs among all graphs which are not minors of any of GK. Okay, you can always find such a set. Then from these two sets, it's again an easy exercise that the following relation holds. So a graph G has pathwidth at most k if and only if G does not contain any of the graph F from this defined set F, calligraphic F. So whenever these two property holds, this property always holds. And this is that on the graph minor relation, any anti-chain is finite. This is from this Robert Seymour's great graph minor theorem. And again, it's easy exercise that F is anti-chain. So from here, you know that F is finite. And also testing whether a given graph is a minor of another graph can be tested in FPT time. Now is quadratic time due to recent result. So using this property, we can have a kind of a heavy machinery algorithm for testing if G has pathwidth at most k. Namely, for every graph F in this set calligraphic F, we test if G contains F as a minor. And the list of the tests is finite. Each test takes FPT time, so the overall test takes FPT time. So can we apply this scheme for matroid testing? So I just replaced what is here. So I replaced all the graphs by matroid here. So this holds, so this holds. But that any anti-chain is finite, this does not hold for matroid in general. So, and also the FPT time for matroid minor testing doesn't hold for general matroid. So actually, infinite anti-chain of matroid under matroid minor relation is not very difficult to construct. And and also its hope is to have FPT algorithm for testing matroid minor in general, because of the following example. So a matroid is binary if and only if it doesn't contain a specific matroid called U24 as a minor. So the binary matroid is characterized by just one forbidden minor. But it is known that any algorithm for testing a binary matroid takes exponential time, given independence oracle. So, it is possible that testing just one minor containment can take exponential time in general. But the good part is that if the matroid is representable on a finite field over a finite field F, then we have this well quasi-order theory, like the Robert. So if if a matroid is F representable over a finite field F, then things are a bit different. So the picture might be a bit different. So okay. So here is here is how you can use this scheme when you know that the matroid is F represented. So now MK is the set of all matroids whose pathwidth is M most K and F represented. And this is again binary closed. And now consider F as a minimal F, not just minimal matroids, but minimal F represented matroids. And from these two, we have this relation. And again, it is already proved by Gillian and Gerard and Whittle some time ago that under matroid minor relation, any antichain of F representable matroids which has bounded branch width is finite. Okay. So we have this. And now F is and if you look at any minimal matroid which is not a minor of MK, then they should have they should have branch width M most K plus 1. If it has branch width K plus 2, then its path width is also K plus 2. So if you take some minor of it, then there should be a minor which has path width K plus 1. So it's not minimal. So they have branch width bounded K plus 1. So F satisfy the condition of this statement. So F is finite. And then we can use some machinery by Hilneny and make minor testing. So now we have FPT algorithm for testing the pathwidth M most K. But here are some problems. So there are too many obstructions for pathwidth M most K. And we know only lower bound. We don't know any upper bound. And there is no known algorithm to generate all minor obstructions. And even if you know the complete obstruction list, then the minor testing algorithm that we use here has gigantic function because it uses the monadic second order logic checking, so it requires huge running time. And also, what is obtained here at the end is only whether it has pathwidth M most K or not, but it doesn't actually produce the layout of the vectors. So this is the state, and our result says that there is a cubic time algorithm to decide a linear layout exists or not of order M most K, and if it exists one, then you can actually produce a linear layout. And yeah, this algorithm is kind of similar and is kind of extension of the dynamic programming algorithm which computes pathwidth for graphs. And it doesn't depend on heavy machinery, so you can actually implement it, and it has a very clean, neat running time, which is single exponential, and it's constructive. And so as a subroutine, we use 3 approximation algorithm for computing branch decomposition of represented matroid, but actually with overhead of O of n, you can get rid of this approximation and make it self-contained. Yes?
What is the running time? What is f of k in your algorithm?
I didn't put in this. So in the middle, I think there will be some number. It's something like 2 to the q times k times theta. Oh, so meaning, so the size of the field and the size of the branch decomposition that you're working on, and the size of the path decomposition that you aim to achieve, they appear in the exponent.
So is your algorithm single exponential?
Yeah. So we do dynamic programming on branch decomposition. So in order to do this, we want to make an encoding of all possible solutions in a way which is compact, so that it's compatible with FPT running time. And you can actually construct the encoding of bigger set from the encoding of the smaller set. That's what we want to do. So, okay, so I'll just try to convey the feel how to create the encoding. So let's consider this very simple case where you have, you have vectors, and you have partitioned them into M1 and M2. And you have suppose you have some encodings of the layouts of M1 and M2, and you want to build something for their union. So the first naive approach is to remember the sequence of dimension for each gap of all possible linear layout. So there will be like n factorial linear layout, where n is the size of M1. Here you have n factorial layout. Of course, this is too many, but this is just for a shot. And you remember the dimension of this gap space. Then, when their intersection is empty, it turns, so this information, this sequence of dimension works as we would intend. So consider any intervening of these two elements while preserving their existing order. So we have this layout. And look at the gap space here between V5 and U4. So this space will is kind of union of the gap space between V5 and V2, which is here, and between U2 and U4, here. And actually, you can prove that, it's not very difficult to prove that the dimension of this space is just simple sum of this and this. So remembering the dimension of this gap space is somehow important, but there are some problems. Of course, there are too many and they are too long. How do you want to make it compact? And another thing is that we didn't consider the case where the subspace spanned by M1 and M2 has non-empty intersection. And this is what we want to handle. So first, I have very little time. So first, in order to compress this long sequence, we use the idea of typical sequence. which is used by Baudelaire and clocks. And almost the same thing also works for us. And the number of typical sequences can be bounded by this nice number. And to handle the boundary space, let's consider, let B be the intersection of the M1 span of M1 and span of M2. Then instead of remembering the dimension of the intersection of this span and this span, remember the dimension of L intersection R minus the dimension of L intersection 1 R, which appears in B. So we remember the dimension sequence which is outside of B. Then you can prove that this actually gives us, it works exactly as we want. So given the dimension sequence of two vector sets outside the shared boundary, and if you just simply sum them up the sequence in the way that in a intended way, then the sum is exactly the intersection space outside B. So this gives you the encoding, which consists of L, R, lambda. L is the space spanned by the vectors on one side. R is the space spanned by the other side. Intersection of B, and lambda is the dimension of the space of the intersection of two outside of B. And this gives you enough information. And there is a way to make it compact, and that gives you a bound on the size of the encoding that you need to handle. So this is how we encode the problem. Okay. So actually, we are able to prove the theorem not just for the linear layout of the vector, but linear layout of subspaces. So instead of taking individual vector, you can actually do it for subspaces, and that gives you that allows us to have new algorithms. First algorithm for two problems. One is exact FPT algorithm for linear rank width, which is like a linear version of rank width. And another is first FPT approximation for linear click width, which is like a linear version of click width. So, yeah, there are two obvious questions. One is, we have this O of n to the 3 factor in the running time. Can it be proved? It seems that there is a chance that it can be proved to n to the w, where w is a matrix multiplication factor. And another question is whether there is FPT algorithm for pathwidth or branch width on general matroid. So using the heavy machinery like minor testing doesn't seem to work, but I'm not sure whether there is no hope for that. I don't know any obvious obstacle for it. Do you know any of it? So this is it. Thank you.
Comments, questions?
So a fine-grained question. Is there any reason to believe that you can't push the dependence, say, down all the way to linear and have all of the Gaussian elimination, matrix multiplication stuff be in terms of K?
Yeah, so actually we do most of the matrix multiplication in terms of K, actually. But at the beginning, we have to set up the boundary space for all the cuts that appear in the tree. That's where this O of n3 comes from. So, yeah, I don't think that, do you know? Okay, I mean, so for example, what we do is we get basis of one boundary space, another boundary space, and once you know the boundary space, their dimension is at most k or 3k. So from these, you can get the basis of any dimension which is the dimension of the parent. And so for that, we use k to the 3 or k to the 2. But at the beginning, for example, maybe for computing the basis, it's not n to the 3. Yeah. Okay, let's talk about it later. Yeah.
Anything else? Then let's thank Eunjung again.